My screen is visible to all of you?
Yes, sir.
Yes, sir.
Okay. So we have started with this new chapter of on fiber optics. We discussed basics of fiber optics, or you can say we discussed basics of how light propagates through any medium. What are the phenomena related to propagation of light? When there is change in medium, then how light bends, and many other things we studied. Then we also talked about guided propagation of light through optical fiber. I introduced to you what is optical fiber and what is basic structure construction of this optical fiber. As we discussed yesterday, it is material of optical fiber. It is generally made up of glass, silica. It consists of two coaxial cylinders, both made up of same material, that is glass, silica. The outer cylinder, which is called cylindrical rod, which is called cladding, that is highly pure silica, highly pure glass. And we dope the inner core, it is doped with some impurities. It is not that pure as cladding is. And why we do this doping? This is done to have change in refractive index, and we want that small change in refractive index. Their relative refractive index change we can also see. We'll see that in today's lecture, and importance of that. So we launch light through this optical fiber. Dimensions of this optical fiber are also important. We discussed them in detail yesterday. All the dimensions, they are in micrometer range order. We also discussed that every ray cannot be propagated, transmitted through the optical fiber. For ray to propagate through the optical fiber, total internal reflection condition at the core cladding interface should be fulfilled. And the rays which will fulfill this condition will only propagate through the optical fiber. So for that we said that it depends on angle of incidence at the core cross section. The incident ray, if it makes small angle with the normal at the core cross section, then it is expected to propagate through the optical fiber. And the larger angles, they do not, or rays which make big angle at the cross section, they do not propagate through the optical fiber. Exactly what is that angle above which light is not allowed by the optical fiber and below which light is allowed or accepted by the optical fiber, that angle is called angle of acceptance. We derived expression for this angle, that is called angle of acceptance. It depends on, as we said yesterday, it depends on refractive indices of core and cladding. So theta A, this angle is called what? This acceptance angle is called, this is denoted by theta A, and corresponding to this angle or the ray which is incident at this angle or launched at this angle into the optical fiber, that is just allowed by the optical fiber to propagate through it. This makes angle at the core cladding interface equals to critical angle for the core cladding interface. If we try to send a light signal or light ray which makes slightly bigger angle than this angle, that is the acceptance angle, then we see that this ray, when strikes the core cladding interface, this strikes at lesser angle than the critical angle. So that light is not, as angle is less than the critical angle, that is not accepted by the optical fiber. All these details we have discussed yesterday. And finally, we derived expression for acceptance angle in terms of sine of theta A, and or you can say acceptance angle theta A is sine inverse theta A. If I am interested in calculating theta A, I can calculate it using this formula, that sine inverse of under root n1 minus n1 square minus n2 square is theta A. So bigger is this angle of acceptance, means bigger cone of acceptance is there, and bigger cone means that more light gathering ability of the optical fiber. It can gather more light. This is independent of dimensions. It has nothing to do with the dimensions, but it depends on this combination of refractive indices. It is depends on N1 and N2. We can discuss more about numerical aperture, or we can write numerical aperture in terms of measurable, or you can say in terms of parameters which are really given to us, or which we know. So those parameters, let me define first new parameter, that is delta, and this new parameter delta is called, this is fractional refractive index change for given optical fiber. And what I mean by fractional refractive index change, it is N1, that is refractive index of core, which is bigger than the refractive index of cladding, minus N2 divided by N1. So this is fraction of change in refractive index as ray goes from core to cladding. So that's why it is called fractional refractive index change. It is N1 minus N2 divided by N1. Generally, this is given. Manufacturers, they know what is the fractional refractive index change for a given fiber, and on the basis of that number, they decide how they can increase or decrease the numerical aperture. So they should have this relation, or we should have this relation, how numerical aperture, it depends on delta, that is fractional refractive index change. Simple mathematics, you can see that term n1 square minus n2 square is involved in this formula of numerical aperture, and in this fractional refractive index change, in this as well, we have this difference, that is n1 minus n2. So by doing some simple mathematics, we can write this numerical aperture in terms of delta. So to do that, let me see what is my numerical aperture. In my numerical aperture, I have n1 square minus n2 square term, which I can write using formula that a square minus b square is difference of a and b and sum of a and b. So I can write it is what it is, n2 minus n1 times n1 plus n2. And one more thing I can do, I can divide this by 2 And let me divide this by N1 to make it delta, that is fractional refractive index change. And I cannot do it as it is. What I have to do is I have to multiply this by the same thing, that is 2n1. So multiplying and dividing this by 2n1, I get this expression where I can identify this as delta. This is my fractional definition of fractional refractive index change. So I can write n1 square minus n2 square is 2n1 times this, that is delta. So let me write that delta, and this is n1 plus n2 divided by 2. This is average of n1 and n2 refractive indices. And I'll give you that example as well. This n1, I said that we simply, how we make this change in because material of core and cladding, दोनों का material एक ही, that is that they are made up of glass. And I said that during when we draw or when we have glass in molten state and we draw that into these wires of or cylinders of optical fiber. So during that time we do doping when we make cladding. And that doping, we do very light doping so that there is slight change in refractive index. So what I mean by this, I want to say that this is difference is very small. That is 1 point. If I say that this is my N1, that is refractive index of core, then it is 1.421. You can say this is refractive index of cladding. Sorry. This should be less, so you can say it is 1.19. Okay, so N1 is approximately equal to N2, and I can say that their mean, that is N1 or average N1 over N1 plus N2 divided by 2, that I can write approximately equal to N1. And if I replace this by N1, so I get 2 delta. किसी का बेटा unmute हो गया है mic. You mute yourself. So now I can write numerical aperture. This is under root n1 square minus n2 square, and which we have written in terms of fractional refractive index change. So I can write it as what it is, 2 delta under root of this. This is this, and under root of this will make it under root this, and this will go. So let me put this inside bracket and let me write. So let me write it again. This is n1 and under root 2 delta. This is numerical aperture in terms of, or we can simply write this as n. This is average of n1 and n2, or you can write it as n1. So one and the same thing. So you can write this is average refractive index under root 2 delta. So we can see here that n1 and n2 are not important in themselves, but only their average, okay, n1 plus n2 divided by 2, and fractional refractive index change or relative difference, that is important. To change numerical aperture, we need to vary these two things, that is n and delta n. That is what manufacturers really do. And numerical aperture can be changed over a wide range, relatively wide range for silica from -0.1 to 0.3 for silica fiber. This is for silica. And for other materials, we cannot make this big change. This is relatively big. This is not big. You can say that this is a difference of only 0.2, but it is relatively big relative to the other materials. So that in silica, we have this freedom of having big range of numerical aperture. We can change it through this 0.3 to 0.4. Let me give you a small example because we have not done anything. If I have N1, which is given to me 1.48 and core refractive index, and refractive index of cladding is 1.46, suppose. So I can find numerical aperture, and this material is what it is, silica. Then I can write, you have formula, simply putting in this formula, I can write that numerical aperture is what it is, 2.something, 2.25 or 2 something, this comes out. So it is in this range of 0.1 to 0.3. Okay, so and as we said yesterday, numerical aperture is what it is, light gathering ability. It is bigger is this cone of acceptance, means more is the numerical aperture, more is the light gathering ability of the optical fiber. More modes you can expect, then there will be more number of paths. We'll discuss that. So this is simply given distribution, refractive index distribution in optical fiber. For ordinary optical fiber, and this is how we give distribution. This means that change in refractive index, or we write refractive index as function of R. R is what it is, radius of core or radius of the optical fiber. This is my optical fiber, and this is axis of the optical fiber, and this is transverse direction, transverse to axis of the optical fiber. So when we move along this transverse direction, then how refractive index varies, this R is what it is, this direction. So that's why it is given in terms of R. When R is, A is radius of my core of the optical fiber. This is optical fiber having core of radius A. So in that case, we can write this is a refractive index profile of my optical fiber. What is refractive index profile? That a refractive index is function of R, and it varies along the transverse direction, whereas it does not vary along this direction. Okay, it varies along transverse direction. That's why I'm saying that this R is what it is, transverse direction, and it is for R less than A, means we are within core. R is less than A means my distance which I have moved away from the axis is less than the radius. So I'm within the core. Then refractive index is N1, and when R is greater, I move a distance which is bigger than the radius of this core. I move out of the core region. Then refractive index, there is change in refractive index, and it goes to N2. So this is a refractive index profile, how we write. So N1 is always, you know all those details, that this N out of N1 and N2, N1 is always greater than N2 because this is core and this is cladding. Okay, and this parameter I have already discussed with you. This is fractional refractive index change, and we can use this to write numerical aperture. Now, going into more details, let us see how light propagates through optical fiber. We know how it propagates through the optical fiber. Let me launch as we have done yesterday, but we'll add something more to this. I have taken 3 rays. This is ray 1, this is ray 2, and I have ray 3 in between ray 1 and 2. I am launching these rays from one end of the optical fiber, and they propagate through the optical fiber through ray 1. It propagates straight without any total internal reflection is there, because it never goes to core cladding interface. It moves along the axis, straight line along the axis of the optical fiber. Whereas 2 and 3 rays, they are moving through this optical fiber through total internal reflections. Yesterday we said that critical angle at the core cladding interface phi c is sine inverse. This is sine inverse n1 n2 over n1. If I ask you a small question, if I give you a small problem to do, and that is for this ray, which makes angle phi c at the core cladding interface with the normal, for this ray, you tell me what angle it makes with the axis of the optical fiber. What I am saying, let me draw it here for you. This is my optical fiber. Axis of the optical fiber. And this is that ray which is launched at angle theta A, acceptance angle. If it makes angle theta A here, then we know that when it will go to core cladding interface, this angle is what it is called critical angle, phi c. And what is angle made by this ray with the axis of the optical fiber? I'm interested in writing what is this angle, this theta. What angle it
90 minus phi c.
It is 90 minus 5.
Yes, it is 90 minus phi c. Or we can say that sine, because we know sine phi c is n2 over n1. And I'm interested in finding this angle, so I can write phi c in terms of this angle as 90 minus phi c is equals to n2 over n1. Your answer is correct, but I cannot measure this angle because I cannot go inside this optical fiber, provided NC is known, that is phi c is known. So let me write that. I can write this as cos of phi c, and sorry, not phi c. This is 90 minus theta c. This is minus theta c because I'm writing phi c. It is 90 minus theta c, and this is also theta c. Cos theta c is n2 over n1. So I can write that phi c, this is angle made by this ray with the axis of the optical fiber, is cos inverse of n2 over n1. So we can say that ray which just fulfills the condition of total internal reflection, or the ray which is launched at acceptance angle, that makes angle cos inverse n2 over n1 with the axis of the optical fiber, and makes angle sine inverse n2 over n1 at the core cladding interface with the normal. Okay, so you can say that this angle is cos inverse n2 over n1, and this angle is sine inverse n2 over. Why this is important? This is important because this is the ray which will travel the longest distance through the optical fiber. And this theta angle, which is angle of any ray with the axis of the optical fiber, it ranges, क्योंकि हम किसकी बात कर रहे हैं, light gathering ability of the optical fiber. We are talking about rays which are accepted by the optical fiber. More rays traveled through the optical fiber means more is the light gain. So this means what? This means that theta, it varies. If I draw it here, let me draw different rays. I can say that this is the ray which moves along the axis. This is at slightly bigger angle. This fulfills the condition of total internal reflection. I have another ray. This also fulfills the total internal reflection. And this is the ray which is incident here at phi c. Now any ray making angle bigger than this with the axis of the optical fiber, that will leak out of the optical fiber, that will not propagate through the optical fiber. So I can decide the range for theta or theta values for the rays which propagate through the optical fiber. Okay, so theta varies from 0 because this is 0, and it varies from 0 to this, and this is what it is, angle corresponding angle here corresponding to phi c at the core cladding interface. So it varies from this to cos inverse n2 over n1. This is range of theta. So all those rays which make angle theta to cos inverse n2 over n1 with the axis of the optical fiber, they propagate through the optical fiber. Okay, so the ray which makes this angle with the axis of the optical fiber, that takes maximum time to travel through the optical fiber, and the ray which makes angle 0 with the axis of the optical fiber, that takes minimum time. Longest path is covered by this ray. This is the ray. It will cover the longest path. This ray will cover the shortest path, and in between they will cover इनके बीच में जो distances होंगे, they will cover those distances. And ये वाली rays, they are not accepted. Anything which makes angle greater than cos inverse n2 over n1 with the axis, that ray is not accepted by the optical fiber. Okay, so now why we have core and cladding, or why material, we choose glass material to make optical fiber. These are some important properties of glass. It is this is in use from last so many years, and it exists in pure form. It exists in pure form, that is important. And it is viscous fluid, and transition temperature, molten state से इसको जब हम solidify करते हैं, that transition range, temperature range is big. And why that transition range, temperature range is required, big range is required, because then we can do what? We can draw this optical this material into thin fibers. We have big range of temperature. It is not that all of a sudden it solidifies. So that is one of the reasons. And जो internal absorptions होंगे वो कम है, इसलिए सिलिका जो है वो लाइट को absorb नहीं करेगा, and it will allow light to propagate without attenuation or without any loss. So extremely low losses is given, some figure is given, it is 96% there is loss of this, not 96% is transmitted, sorry, it is not lost, transmitted after propagating through 1 kilometer of the fiber. And material इसलिए भी हम चूज करते हैं क्योंकि उसका स्ट्रेंथ अच्छा होगा. इट इज ऑप्टिकल फाइबर, तो जहां ऑप्टिकल फाइबर होगा तो इन्वायरमेंटल इफेक्ट्स हैं, कुछ और हैं, तो स्ट्रेंथ शुड बी गुड. So strength is also good. It is about this pounds per inch square. Okay, so these are some. So now, very important thing. Optical fiber की तरह nature में what is there? It is your eye, जो retina है हमारे eye का, which consists of number of rods and cones. You can see here this part is what it is. That you can see rods and cones here, and this is retina of your eye. And these cones, these rods, they have structure of these rods and cones are identical or is identical. Structure is identical to structure of optical fiber. Here, this is bigger picture of these rods and cones, and it is exactly like optical fiber. What is structure of optical fiber? In optical fiber, we have a inner part which is having high refractive index or bigger refractive index than the outer part having lesser refractive index, और ये dielectric material है आपका. And इनका size क्या है? It is micrometers. Same is true, exactly same is true for these rods in your retina. So light is absorbed by these rods, these retina, and it is converted, that light is converted into electrical signal, and that is sent to your brain. So nature में optical fiber is already there inside your eye to propagate light. So exact description if we see, so it is what? Retina of your eye. It consists of large number of rods, cones, which have same type of structure as the optical fiber. And they consist of dielectric cylindrical rods surrounded by another dielectric of slightly lower refractive index. तो वहाँ पे भी total internal reflected light signal जो जाएगा, which gets further converted into electrical, that travels, that is absorbed, and that travels by this phenomena. And their size is also of the same range. It is what you can see here. Core diameter are in the few micrometer hai, or the light absorbed in these light guides generate electrical signal which is transmitted to brain. And this enables us to see the outside world. So this is a very interesting thing. Then I have already done this. This is you can write numerical aperture sine of theta a, or here we are writing theta im. So one and the same thing. It is sine theta a, which is under root n1 square minus n2 square. I can write that in terms of fractional refractive index change, and this you can call it average of n1 and n2. And then you can approximately you can write that this is equals to this, you can replace this. Now we want to estimate numerical aperture of the fiber. There are two techniques. We have one of the techniques is how we are interested in measuring what is numerical aperture. Okay, we do not have information about, you can say, okay, sir, numerical aperture, it is n1 square minus n2 square under root. You give me values of n1 and n2, and I can give you what is the numerical aperture for the given fiber. But I do not want that, or I do not have information about n1 and n2 or their values. So I want to know what is a refractive index, numerical aperture of my optical fiber. So for that I use laser light. I take LED here, light emitting diode or some laser, and we put here some power meter to measure intensity of this light. Okay, then we do not have anything here. It sends light and it is detected here. And so when we measure power of this signal, that is, let me call that is P naught. Okay, P naught means there is no other medium. It is like vacuum or free space. Then we put optical fiber here. Second time we do measurement, we put optical fiber here. Then again we measure power here. And this ratio, numerical aperture is under root P power with optical fiber placed between LED and power meter and divided by P naught when nothing is there between these two. So sometimes with numerical may something can be asked like this. Then we have another experimental technique to measure or to estimate what is the numerical aperture of the given optical fiber. One more experiment we can do and we can see what is the numerical aperture. For that, we take this as my optical fiber. I launch light from this side into the optical fiber at all possible angles. And if light travels through all the modes, possible modes through the optical fiber, then we can see what light coming out of the optical fiber that is seen on a screen, and it makes this illumination, circular illumination on the screen. We measure diameter of this circular illumination, and we also see what is the distance between the screen and the optical fiber. Then we can measure this angle. This is angle between the direction of the axis of the optical fiber and the line joining optical fiber with this end of the this circle. That we can write in terms of these two distances, because this theta, I can measure this in terms of, I can write this as tan of theta, which is d divided by 2z, or we can write which is half of d, this much, that is perpendicular divided by base. So you can write it as half of d divided by z, this distance. And then theta is tan inverse of d divided by 2z. What is this theta? Anything launched here at theta angle that comes out of the optical fiber at the same angle theta. Okay, you can see it from geometry. So we can see that this is the maximum angle. है ना, इसके बाहर कोई ray नहीं आया, तो that means nothing is launched greater than this angle. So this is theta A, angle of acceptance. Once you know angle of acceptance, then what sine of that angle of acceptance, sine of theta A, is what? In this case, it is sine of tan inverse d divided by 2z. So this is numerical aperture. We have estimated numerical aperture by simply using our optical fiber and propagating light through optical fiber and seeing what is coming out, and we see geometry of that which is coming out of the optical fiber, and we can estimate numerical aperture for the optical fiber. Okay, so that description is given here. You go through this, and this is how we calculate. This is sine of theta A, acceptance angle. This is tan inverse d divided by. Okay, so that means angle of acceptance is this. Then we have allowed values of angle of propagation. जैसे मैंने अभी कहा कि कौन कौन सी allowed values हैं angle of propagation with the axis of the optical fiber or at the core cladding interface. That is These are all allowed values, and again we'll be emphasizing on that anything launched at angle less than the acceptance angle, those are the allowed rays to propagate through the optical fiber. And what angle that makes here, that is similar to what I have told you. This angle is equal to this. So if somebody asks you what angle is made by the ray with the axis of the optical fiber, same as the angle made by the same ray with the core cladding interface. So critical, if this angle is theta c, means it is launched at angle equals to theta a, acceptance angle, then that ray, or which makes here phi c angle, that is critical angle, यहाँ पे जो angle बनाएगा, that is cos inverse. This angle is sin inverse, or let me draw it nicely. What I am saying is, it is just geometry of, you can do it. And this is this is theta a, then this is theta a. This angle is called, this is called theta c, and this is what, this is phi c. This is phi c, and this phi c is sine inverse n2 over n1. This theta c is cos inverse n2 over n1, and we are adding one more thing to it, that this is also equal to cos inverse n2 over n1. So this is sine inverse n2 over n1, and this is cos inverse n2 over n1. Okay. So with the core cladding interface, angle made by the ray which is just accepted by the optical fiber is this much, or it varies from 0 to sine inverse n2 over n1. So we have demonstrated, or we can demonstrate an experiment where we can see number of modes propagating through the optical fiber. So this is that experiment. In this experiment, you can see that here we have optical fiber. This is my optical fiber. Sorry, this is optical fiber. Light is launched through this optical fiber. This is source is big, but we are focusing this light at the core cladding interface because it is micrometer size. So that's why it is shown like this. And it propagates through the optical fiber. We put a prism of very high refractive index close to this core so that we can disturb the condition of total internal reflection and light leaks out of the optical fiber. We want these modes, which are allowed modes, which generally do not leak out of the optical fiber. We force them to leak out of the optical fiber so that we can see on a screen कि कितने modes थे, different angles पे. This will come out, these rays will come out at different angles because they are incident at different, you can see 0 to cos inverse n2 over n1. This is the range of the angle. So you can see here different light on the screen. So that means there are number of modes are allowed here. This is type of multi-mode optical fiber. And here, this is what you can see, that only one mode is allowed, one direction is allowed to propagate through this optical fiber. So we can do these small experiments. It can be done anywhere, and you can see, we can decide about the modes. So why I discuss this with you, because next topic is what this topic where we categorize optical fiber into different types on the basis of their refractive index profile, and also on the basis of number of modes which propagates through the optical fiber. When we keep this as criteria to divide or to classify our optical fibers, that is, we say that criteria is the number of modes, then we can categorize optical fiber into two, that is multi-mode optical fiber and single mode optical fiber. Either propagation direction is only one direction is allowed, so that is it is called single mode. If more than one directions are allowed, rays can move through more than one directions through the optical fiber, then it comes under the category of multimode optical fiber. And we can also categorize optical fibers on the basis of their refractive index profile. As I said earlier, that transverse direction along refractive index with change is observed, and there is no change in the refractive index along the axis of the optical fiber. So I'm choosing this as this is transverse direction, transverse to the axis. This is refractive index axis. No, sorry. This is refractive index axis, and this is my direction along which I'll move. This is R. Okay, this is not direction, but I'm plotting it. This has nothing to do with this direction. Don't get confused. Okay, so this I have drawn parallel to this so that I can match it with this. That if I move from the center, this is the center of the core. If I move away from the center of the core in any direction, up or down direction, I see that up to this refractive index is same here. This is the value of refractive index along this axis. And then there is change in refractive index at this, that is core cladding interface. Refractive index changes from this value. You can say that this value is N1 and it changes to N2. And this type of refractive index profile makes this step index, because there is step in this plot or in this refractive index profile, and step is at core cladding interface, and within the core there is no change, or the refractive index is constant. So I can say that this is a constant. This is constant for R less than A. And this is also constant for R greater than A. Then where is the change? It is exactly at R. So R it is not equal to, you can say this at R equals to A. Okay, so change happens only at the interface. So it is a step index fiber. This type of fiber is called what it is called step index fiber, because change from core to as we move from core to cladding. Then we have another type of refractive index profile. This you can see that up to here, this is core. So even within core, the refractive index is not constant. It is continuously varying. It is maximum at the center of the optical fiber. This is maximum value of refractive index, and then it decreases. Either we move up or down, it decreases, and then it becomes what it becomes, N2. Okay, so it is constant here, but it is not constant here. Within the core, it is not constant. Within the core, it is function of R. You can say that this is function of R for R less than A, and this becomes constant as you move out of the optical fiber, or you move out of the core region of the optical fiber. Diagrammatically it is shown. You can see here they have shown it with color. They have shown uniform color for core, so means uniform refractive index, same refractive index. Here you can see that it is central part is darker than the outer region, so that it is shown that refractive index is more at the center, and then gradually it fades out or it decreases, and as we move towards the core cladding interface. Dimensions are also given. You can see these are the dimensions. And then we have third category, which is in terms of modes as well, you can see this is multi-mode optical fiber. Sorry, these are multi-mode optical fibers, and this is single-mode optical fiber. It is step index. I can see both the properties. Mode is single, and refractive index varies in a step. So it is step index or single mode step index fiber. Single mode step index fiber. Okay, and this is what this is. Multi-mode modes. There are number of modes, allowed modes. So this is multi-mode step index fiber, and this type of fiber is called graded index. ये हमने पहले भी कहा कि refractive index is not same. It varies gradually. Then refractive index is gradually changing. That's why it is called graded index optical fiber. It is multi-mode graded index optical fiber. So you can see different modes in this as well as in this. Here we can see that a ray goes straight up to core cladding interface, because change in refractive index is only at that interface. So that's why bending is only at the core cladding interface, and that bending is also total internal. We know that it is total internal reflection. So rays, they are moving in a zigzag manner, and they remain straight between the two successive total internal reflections. In case of step index fiber, in case of multi-mode step index fiber. And in case of single mode step index fiber, it remains straight from one end to the other end of the optical fiber. Not only between two, there are no total internal reflections, so we cannot talk in terms of two successive total internal reflections here. And this is what this is graded index fiber, where there is gradual change in refractive index as ray, if we say that it starts from here and from the center of this optical fiber, as it moves away from the center or moves in transverse direction away from the center of the optical fiber or from the core, then it gradually bends. है ना, हमने अभी पहले भी डिस्कस किया था. तो रिफ्लेक्टिव इंडेक्स जैसे जैसे आप दूर जा रहे हैं, दैट इज डिक्रीजिंग. So you can imagine it as a different layers of finite width, but refractive index is decreasing as you move up. Then you can plot, you can see how it should bend. Light should bend. It will bend away from, as it will move away and away from the core. It will bend away from the normal, because it is going into the rarer medium. As it is going in the rarer medium, it bends away from the normal. So as it is moving, it is bending away from the normal. So then you can see that it is bending like this, and then it gets यहाँ से bending जो है वो it is towards this. Why? Because अब ये bend होते होते कहाँ पहुँच गया है? It is parallel to the this axis of the optical fiber, and then it starts like this. It starts going back towards the denser medium. Okay, so this is how we अरे अच्छा, नेटवर्क मेरा कुछ चला गया था. कब? अभी गया था कि काफी देर हो गई?
अभी गया था सर.
अभी गया था.
जस्ट अभी गया था. मैंने कंक्लूड कर दिया था, है ना?
यस सर.
कि नहीं किया था? लास्ट स्लाइड पे कुछ कंक्लूजन मेरे
कर दिया था,
है ना? मैंने आपको कह दिया था कि लेट अस स्टॉप, है ना?
यस सर.
Okay, fine. So if you have anything, any queries, you stay back, you ask your queries, and rest of you can hang up.
सर एक्सक्यूज मी सर.
हाँ बेटा. Yes.
Sir, for 2 days the government had banned the use of internet in the Jharkhand, sir. That's why I couldn't attend the previous classes.
Okay. For डेट्स मुझे बता देना कौन कौन सी डेट्स थी, है ना?
So previous 2 days.
Okay, it was Monday and Tuesday.
Yes, sir.
Your roll number is 26.
Yes, sir. BMA 026.
हाँ, तो ये यश, are you there? Yash is not present. चलिए कोई नहीं, I'll keep this in my mind and मैं आपका I'll do it accordingly.